Okay, good morning class. Today we are going to learn about effect of water table on bearing capacity of the soil. So firstly we'll see what do you mean by water table, then what is the effect of that water table on any level between the footing and the ground level, and what will be that particular effect on the safe bearing capacity of the soil which we have calculated, or which we are going to calculate with respect to this rise and fall of effective of water table. So when the water table is above the base of the footing, the submerged weight gamma dash should be used for the soil below the water table for computing the effective pressure or the surcharge. When the water table is located somehow below the base of the footing, the elastic wedge is partly of moist soil and partly of submerged soil, and a suitable reduction factor should be used with the wedge termed 1 half gamma Bn gamma, since it uses effective unit weight. So in first case, water table located above the base of footing. So water table located at the base of footing. So what does it mean? This is your ground level, this is your column, and this is your flat footing with width B, and this is your foundation depth DF. So if the water table is between your footing above the base of the footing, this WT means base of the footing. So what will be the bearing capacity of the soil? So for calculating this, you should know the depth above water level and depth below water table at the base of footing. So that this will be determined by dW, and this will be say that this is small a. So let us see what happens when it is located there. The effective surcharge is reduced as the effective weight below the water table is equal to the submerged unit weight. Therefore, Q equals to dW gamma plus A into gamma dash. So Q is the surcharge, or Q you can say that it is surcharge water level weight. So it is given by dW gamma. So this is your dW into the unit weight here of the soil which is dry. So we can say that it is a bulk unit weight. So that will be gamma into dW. ये हो गया है. अब इसके नीचे का क्या रहेगा? तो here there is a water table, so unit weight of this soil will be submerged unit weight of the soil, so it is said plus A into gamma dash. So plus A into gamma dash. So Q, total Q surcharge, it is calculated by unit weight of this soil above the water table, which is gamma, with respect to your dW depth up to your water table. After that you are having the submerged unit weight gamma dash into the depth up to your base of the footing, which is A. So this is how you are calculating this Q, effective surcharge. So where dW is the depth of water table above the ground surface, and A is the height of water table below the base of the footing. Therefore it is given by total dF minus dW. So from diagram itself it is seen that this total is your dF minus dW will give you the total height of water table below the base. So therefore the ultimate bearing capacity is given by Qu equals to C dash Nc plus gamma dash dF plus gamma minus gamma dash dW into Nq plus zero point 0.5 gamma dash Bnq. Now here you have to see that the basic formula is Cnc plus gamma nq plus zero point 0.5 gamma bn gamma. So nc is for cohesion, nq is for surcharge, and n gamma is for unit weight. N is the bearing capacity factor given by Terzaghi. So they are called as bearing capacity factors of Terzaghi or Terzaghi's bearing capacity. So factors. So these are NC, N gamma, and NQ. If it is having dash, then they will be divided into two different types: local shear failure or general shear failure. So we are seeing only the flat footing here. So there will be zero point 0.5. If you are having circular footing, if you are having rectangular footing, then this zero point 0.5 is different. So basically now we are going to take it as zero point 0.5 for flat footing. Now if dw equals to 0, that is A equals to df, then q u will be c dash nc plus gamma dash df nq plus zero point 0.5 gamma dash b nq. So this will be the condition when dw is 0. That means your water table is at ground level itself. Then if A equals to 0, that is df equals to dw, then qu equals to c dash nc plus gamma df nq plus zero point 0.5 gamma dash b nq. So whatever may be the condition, if dw is 0 or A is 0, you have to consider the same value with respect to df, and the question of calculating the ultimate bearing capacity formula will be this for both the cases. This was the first case when the water table was located above the base of the footing. Now second case is the water table located at the depth b below the base. Okay, so this is the diagram. This is your ground surface, this is your column, this is your base of the footing. So what happens, this is the width, and you are saying the case is that the water table located at the b depth below the base of the footing. So this is your base of the footing, and at b depth the water table is located here, and from here to base of the footing your foundation depth is df. So what will be the condition? So let us see what happens. If the water table is located at the level base of the footing or below it, the surcharge term is not affected. However, the unit weight is modified as. It says that surcharge load will not affect, means the load in between the width of the footing, मतलब फाउंडेशन डेप्थ में अगर आ रहा है आपका वाटर टेबल या उसके नीचे है तो भी उसका सरचार्ज लोडिंग में कोई फर्क नहीं आएगा, लेकिन there will be definitely a change in your unit weight as it is below. So what you have to calculate is the unit weight up to the point B, the height B. So gamma bar equals to gamma dash total unit weight इसके नीचे का plus B upon B gamma minus gamma dash. So B is the depth of water table below the base and B is the base of width of the footing. Therefore, Qu equals to C dash Nc plus gamma df Nq plus zero point 0.5 B gamma dash plus B upon B gamma gamma minus dash gamma dash into N gamma. Okay. So if we say that B equals to 0, that means water table is at the base here itself at df, then what will be your Qu? So Qu will be equals to C dash Nc plus gamma df Nq plus zero point 0.5 gamma dash B N gamma. When B equals to B, मतलब ये B is equals to the width of this footing, that is water table at depth B below the base, then what happens? Qu will again remain the same. So it shows that if the water table is below or it is in between the depth of the footing, your effective loading doesn't change. That will be remaining the same as it is calculated in case number 1. But what you have to do, if it is the condition, you have to add the reduction factors. So Qu, you have got this formula. So formula is Qu equals to C dash Nc plus gamma df Nq plus zero point 0.5 B gamma N gamma. Hence, the groundwater table is located at a depth B equal to or greater than B. There is no effect on the ultimate bearing capacity. For intermediate positions, interpolation of reduction may be made. For any position of the water table equations are given below. So kindly see the equation where you have to add the reduction factors. So here you have to add the reduction factors. Qu equals to CNC plus gamma dNq into Rw1 plus half means zero point 0.5 gamma B and gamma RW2, where RW1 and RW2 are water reduction factors. So how you will calculate RW1? It will be with respect to D, and RW2 it will be respect to B. So that will be given by 0.5 1 plus ZW1 upon D. At ZW1 is equals to 0, RW1 equals to half. And if ZW1 is equals to total del D, then RW1 will be equals to 1. Now, if RW1 equals to 0.5 1 plus ZW2 upon B, if ZW2 is 0, RW2 will be 0.5, and if ZW2 equals to 0, RW equals to 1. So this is the condition. When water is much below or greater than depth, then no effect of water table is to be considered. So this is the condition. If there is water table above the base of the footing, RW1 has to be considered, ZW1 will come. If it is below the footing, then RW2 will come and ZW2 you have to consider. But when water is much more below at the required depth, then there will be no effect of water table for the shallow foundation. Next is your Scrimton's analysis for cohesive soils. So what do you mean by cohesive soils? Which is having the property of swell shrink. When you add water and remove water, there will be the property of the soil to swell and shrink. So if this type of soil is there, symptoms, Grimstorms was one of the scientists who has given certain formulas to calculate the values of bearing capacity. So let us see what symptoms say. Symptoms 1951 showed that the bearing capacity factor NC in Kazaghi's equation tends to increase with depth for a cohesive soil. Phi u equals to 0, C equals to Cu. So figure 4 shows the variation of NC with dF upon B. So here is your figure 4. So we'll see what is that. So dF by B ratio. So where is your dF by B ratio? This is your dF by C ratio, B ratio, and this is your NC. So for ratio for strip and circular or square footing. For strip footing, the value of NC is equals to 5.14. For the surface footing, maximum value of 7.5, and dF by B ratio equal to or greater than 4.5. For square and circular footings, the value of NC is equals to 6.2 for surface footing. The maximum value of about 9 is attained for dF upon B ratio equal to or greater than 4.5. The curve and square and circular footings can also be used for rectangular footings using the following relation. NC rectangular equals to NC square 0.484 plus 0.16 B upon L. As it is rectangular, then you can say it is B upon L. If it is square, then it will be B upon B. Alternatively, the curve for the strip can be used making use of the following relation. NC equals to NC rectangle equals to NC strip 1 plus zero point 0.2 P upon L. The following approximately relations can be used for the determination of NC for different dF upon B ratios. So those are dF upon B less than 2.5, then NC equals to 5, 1 plus zero point 0.2 dF upon B into 1 plus zero point 0.2 B upon L. Second case, dF upon B greater than or equals to 2.5, NC will be equals to 7.5 1 plus 0.2 B upon L. So for calculating the ultimate bearing capacity, if phi equals to 0, NQ will be equals to 1 and N gamma equals to, okay, N gamma equals to 0. So when this is the condition, then QNU is given by CUNC plus gamma and gamma D gamma. So therefore the net ultimate bearing capacity becomes QNU equals to CU into NC. Since your value of N gamma becomes 0 and NQ remains the same, then net ultimate bearing capacity for cohesive soil will be Cu into NC. So this is used for the determination of the net ultimate bearing capacity of footings on cohesive soils, taking NC value given by scrim term. It may be mentioned that Tarzagi's value of NC is applicable only for shallow footings, DF less than B. Scrimterm's value can be used for all the value of DF upon B ratio. So look at the figure, this graph. The graph is given for strip and square or circular footing. So DF upon B ratio is there and NC is there. When you calculate the value of DF upon B, from this curve you can calculate directly projecting on this curve of strip or whatever footing, rectangular, square or circular footing, you can project on the y-intercept and you will get the value of NC. So you can calculate the ultimate bearing capacity QNU by calculating C and NC from this graph. Now, scrim terms settlement of foundation. So settlement under loads. Foundation settlement under loads can be classified into three types. Immediate or elastic settlement, which is given by SI. Immediate or elastic settlement takes place during or immediately after the construction of the structure. It is also known as the distortion settlement, as it is due to distortions and not the volume change within the soil foundation soil. Although the settlement is not truly elastic, it is computed using elastic theory, especially for cohesive soils. So, immediate or elastic settlement, it means that whenever you are carrying out the constructions and it is with respect to the settlement of distortion means impact loading. So whenever there is an impact loading, it is not changing the shape and size of the soil. Just because of that particular distortion loading, the volume is not changing. Since the soil is under pressure, then you can say that it is immediate or elastic settlement, and it is said to be elastic for cohesive soil because it is temporary phase. Next is your consolidation settlements (SC). This component of the settlement occurs due to gradual expulsion of water from the voids of the soil. This component is determined using Tarzagi's theory of consolidation. The consolidation studied in unit number 5 of GT1. So the gradual loading of the structure gives the birth to the removal of water from the voids of soil to the water table. So that is known as your consolidation settlement. Next is secondary consolidation settlement SS. This component of the settlement is due to the secondary consolidation. These settlements occur after the completion of primary consolidation. It can be determined from the coefficient of secondary consolidation. The secondary consolidation is not significant for inorganic clays and silty soils. The total settlement S is given by S equals to Si plus Sc plus Sr. Next is settlement due to other causes. In addition to settlement under loads, the settlement may occur to a number of other subsoil which occur to the number of other causes. So what are those? So first is underground erosion. Underground erosion may cause formation of cavities in the subsoil which when collapse cause settlement. So from surface, if you are seeing the plain ground, but when you dig, there is a vacuum or open space or empty space at the depth of soil sometimes. So that is known as your cavities. So those cavities which is having the total voids in that air voids or water voids, but when they collapse down and the settlements takes place. Next is your structural collapse of soil. Structural collapse of some soils such as saline, non-cohesive soil, gypsum, silts and clays and loess may occur due to dissolution of materials responsible for intergranular bonds of grains. So what happened in mentioned soils when water added or removed, the grains of the soils they contract and they expand. So when this happens, there will be the collapse of the soil, the breakage of the soil. So that is known as structural collapse of the soil. Then thermal changes. The thermal changes cause shrinkage in expansive soils due to which settlement occurs. Temperature changes, there are three seasons, so whenever in seasons there is increase in the hot or dry weather cycles are there, so with respect to that there will be the shrinkage in expansive soil in hot and dry weather, so that will try to create the settlement of the soil. Frost heave occurs if the structure is not founded below the depth of frost penetration. Frost is where there is ice, and because of this ice, the soil will try to thrust and they will try to move in the upward direction. And when it will try to bulge out, then it is known as the first heave, and which will try to settle down the underlying structure. Mining subsidence. So subsidence of ground may occur due to removal of minerals and other materials from the mines below. Read the 3.789. Mining subsidence of ground may occur due to removal of minerals and other materials from the mines below. Landslides, if landslides occur on unstable slopes, there may be serious settlement problems. Creep, the settlement may also occur due to the creep on clay slopes. And last point, can you read? Okay, changes in the vicinity. So if there are changes due to the construction of new building near the existing foundation, the settlement may occur due to increase in the stresses. Suitable measures are taken to reduce the settlements due to all the above causes. So there are nine factors which are considered for the settlement. So whenever such question comes, you have to give the explanation by rendering the all the nine factors which are required for the settlement. Now next topic is your bearing capacity of square and circular footing. Uh, these are the most important formulas which we are going to consider while solving the numericals. So kindly pen down on some pages. Take one page and write down all the formulas for square footing, circular, rectangular, so that while we solve the problem, which formula you have to use, there will be no confusion. So first is your square footing. QU equals to 1.2 C dash NC plus gamma DF NQ plus zero point 0.4 gamma B N gamma, where B is the dimension of each side of footing. Second, circular footing. QU equals to 1.2 C dash NC plus gamma DF NQ plus zero point 0.3 gamma B N gamma, where B is the dimension of each side of footing. The bearing capacity factors NC, NQ and N gamma are the same as that for the strip footing. Intermediate settlement of cohesionless soils. So as cohesionless soils do not follow Hooke's law, intermediate settlements are computed using a semi-empirical approach proposed by Sismontan, Mann and Hartmann 1978. SI equals to C1 C2 Q bar minus Q summation 2B Z equals to 0 Iz upon Es delta Z, where C1 equals to correction factor for the depth of foundation embankment 1 minus zero point 0.5 Q upon Q bar minus Q. C2 equals to correction factor for creep in soils equals to 1 plus zero point 0.2 log to the base 10 time in years upon zero point 0.1. Q bar equals to pressure at the level of the foundation. Q equals to surcharge equals to gamma into dF. Es equals to modulus of elasticity and Iz equals to strain influence factor. The value of Iz at depth Z equals to 0, 0.5 B and 2B are respectively equal to zero point 0.1, zero point 0.5 and 0. For rectangular foundations with L by B ratio between 1 and 10, interpolation can be made. The value of Es can be determined from the standard penetration number n using the following equations given by Sigmundman 1970. Es equals to 766 Newton, n kilonewton per meter square. Alternatively, it can be estimated from the static cone penetration resistance QC as Es equals to 2QC. So from the diagram, if you can see, the values can be calculated for required Z with respect to the width B. So for the procedure, the computation of the intermediate settlement, the soil layer is divided into several layers of thickness delta Z up to a depth Z equals to 2B. So this is your last depth 2B, zero point 0.5, 1, 1.5 and 2. So the depth in between these factors are calculated and the pressure distribution diagram is made with respect to Es and the effect is said to be delta Z. Alright. So the immediate settlement of each layer is computed using equation of SI, taking corresponding values of Es and Iz. The required intermediate is equal to the sum of settlements of all individual soil small layers. All these are to be added and this will give you the required settlement. Accuracy of the foundation settlement prediction. The prediction of the foundation settlement are the soil deposits are sudden, isotropic and linear elastic. The deposits are generally non-homogeneous. So first prediction is Soil is isotropic, sudden isotropic. So first it is not isotropic, but whenever you are doing any structural member construction, then it will become sudden isotropic and linearly elastic. First it will be a straight line, then it will, if you remove, then it will come to its original position. So you can say that it is having a linear elastic mode. And then the soil is homogeneous, that means non-cohesive soils, non-homogeneous, their bonding is not so good. Next is, it is not possible to estimate the increase in stresses caused by loads. The Buzenic solution gives only approximate results. So Buzeni's equation or Buzenic solution for one layer sigma z we have calculated in stress distribution chapter of unit number 4 GT1. Next is for estimation of the settlement due to consolidation. It is not possible to locate exactly the drainage spaces. For computation of immediate settlements, it is not possible to estimate the correct value of the modulus of elasticity. The rigidity of the foundation is usually neglected and the pressure distribution is assumed to be uniform. It is difficult to obtain undisturbed samples of cohesionless soils. Semi-empirical methods do not give accurate results. Settlements may occur due to causes other than that due to loads. It is not possible to estimate these settlements accurately. Despite all the above reasons, the settlement is in most cases, can be estimated to an accuracy of about 25 to 30%, which is good enough seeing the proximity of the problem. So this was all for today. From next class, we are going to learn about the numericals based on your formulas. So this was all for today. If you have any problem, you can contact